Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Can you find area of the green shaded square? Take a moment to study the figure. Then let us uncover the key geometric ideas that make the solution click. Two identical circles with centers P and Q rest on the same baseline and just touch each other. A small green square is wedged into the gap, sitting on the line with its right-hand corners D and E pressing against the circles. We want the area of that green square. Each circle has area 100 pi. Since the area of any circle is pi times its radius squared, we can write pi r squared equals 100 pi. That single equation pins down the radius, which every later step depends on. Dividing both sides by pi cancels the pi and leaves r squared equal to 100. We isolate r squared first because it is one clean step toward the radius. Taking the positive square root gives r equals 10. A radius is a length, so we keep only the positive value. Both circles therefore have radius 10. Draw the radius from P straight left to A and from Q straight left to B. A circle that rests on a line meets it where the radius is perpendicular to the line, so these two radii run horizontally onto the base. Because each of those radii is 10 and points straight to the right, the centers P and Q each sit exactly 10 to the right of the baseline. Fixing their position sets up the coordinate frame we will use to locate the square. The two circles touch each other at the middle point, C. Draw the segment from P to Q. Because the circles are tangent, C lies exactly on this segment, right between the two centers. Aha! The circles touch externally at C, so segment PC and segment CQ lie on one line, and each is a radius. Therefore, the center span segment PQ is exactly 2 radii, 20, which fixes the symmetric coordinate positions before the square enters the calculation. Mark the point O at the middle of the gap on the baseline, and draw the segment from O out to the touch point C. Take O as the origin, with the baseline as one axis and the direction perpendicular to it as the other. By symmetry, the line OC is the mirror line of the whole picture. With O as origin, P sits 10 up and 10 to the right at minus 10, 10, while Q sits 10 down and 10 to the right at 10, 10. Now every point has honest coordinates to compute with. Because the figure is mirror symmetric about the line OC, the green square must straddle that line evenly. Its base is centered on the origin, which lets us describe all four corners with a single unknown. Call the side of the square S. Then its base runs from minus S over 2 to S over 2 along the line, and its height extends from 0 to S. One unknown now controls the whole square. The bottom right corner E therefore lands at S over 2S. This is the corner that presses on the bottom circle, so it is the one we track from here on. Aha! Once symmetry places the square, its bottom right corner E has coordinates determined entirely by the side S. Because E lies on the circle centered at Q, the single radius QE equals 10 condition controls the whole square without revealing which algebraic root will fit. From E, move straight across to the level of Q and mark the foot F. Then draw the two legs segment EF and segment FQ. This makes a right triangle with the radius QE as its hypotenuse, so we can use the Pythagorean theorem. Vertical leg is the difference in x, s over 2 minus 10, and the horizontal leg is the difference in y, s minus 10. Squaring will remove the signs, so we only need these two differences. By the Pythagorean theorem, the two legs squared add up to the hypotenuse squared, So s over 2 minus 10 squared plus s minus 10 squared equals 10 squared, which is 100. Expand the first square. S over 2 minus 10 squared is s squared over 4 minus 10s plus 100. We expand one square at a time to avoid slips. Expand the second square. S minus 10 squared is s squared minus 20s plus 100. Now, both squares are in plane polynomial form. Add the two expansions. The s squared terms combine to 5/4 s squared, the s terms give minus 30s, and the constants give 200. All of that equals 100. Bring the 100 to the left so the equation reads equal to 0. 5/4 s squared minus 30s plus 100 equals 0. A quadratic is easiest to handle once it is set to 0. Multiply every term by 4/5 to clear the fraction and make the leading coefficient 1. The equation simplifies neatly to s squared minus 24s plus 80 equals 0. Compute the discriminant, b squared minus 4ac. That is 576 minus 320, which is 256, a perfect square, so the roots will come out clean. The square root of 256 is 16, so s equals 24 plus or minus 16 all over 2. That gives two candidates, 20 or 4. A side of 20 would span the whole distance between the centers and could never fit in the little gap. So the wedge square must have the small side, 4. Check it. With side 4, the corner E is at 2, 4, and its distance to Q at 10, 10 squares to 64 plus 36, exactly 100. The corner really does lie on the circle. So the answer is 16. That completes the solution. A good geometry problem often has more than one beautiful solution. If you see a genuinely different construction, a high-level idea that leads to another solution, or a thoughtful adaptation of an existing method, share it in the comments. Even a rough idea is welcome. A sketch of the key move is enough. We greatly appreciate these contributions. With your permission, we may feature the approach in a future Viewer Solutions episode and acknowledge you by name or channel handle. Thanks for exploring geometry with GeoMethod.